This video will kind of look at a blast from the past for horizontal asymptotes. And really the question that we're going to be asking here is how would we compute a limit of this form? So if x goes to infinity, what happens to a function? And that's essentially asking what are the horizontal asymptotes. And I say asymptotes because it is possible for the function to have two different ones. If you go towards minus infinity, you can get a different answer. Okay, so let's just look at a quick example here. Let's say that f of x is 10x plus 1 divided by 5x minus 4. Now when we started computing limits, we did this with sort of a bunch of numerical experiments, and so this is going to be no different. And so what I'm going to do here is make a quick little table, and we're just going to compute a bunch of values and see what happens. So I'm going to put x in one side and f of x in the other, and then we're just going to compute a bunch of stuff. Okay, so here we'll go x, and here we'll go f of x. And what I'm going to do is plug in successively larger numbers. So I'll start with 10 to the 0, which is 1, and then I'll do 10 to the first, which is 10, and 10 to the second, which is 100, and 10 cubed, which is 1,000, and hopefully you get the idea at this point. And then let's just go ahead and do one more here. So 10 to the 6th will be the last one that we do. Okay, and if I plug all of these things into the function, not too bad to do, just need to do some kind of calculator action. Google might speed this up for you, or Wolfram Alpha. Okay, so if I plug all these numbers in, what do I get? If I plug in 10 to the 0, this one we can compute really easily because that's just 1, so I get 11 on top, and 5 minus 4 is 1 on the bottom, so I get 11 on the nose, but I'll go ahead and put all 5 significant digits there in the decimal point. Okay, and then I'm just going to do the same thing for all of these. So I computed all these out beforehand, real easy to do, and so I got 2.19565 for this one. And oh, and by the way, in all of these I rounded to the 5th decimal place. Got to stop somewhere. And then for the next one I got 2.01815, and then 2.00180, and then 2.00018. And then for 10 to the 5th, I got 2.00002. And then lastly, for the other one, I got 2 and then rounded to 5 decimal places. It looked like it was 2 on the nose, so there was a 2. There were some digits further out here. Okay, so looking at this, what we want to determine is what happens if the x's are getting really, really big. Well, our x's here are getting progressively bigger from 1, 10, 100, 1,000, and so on, so they're going up by powers of 10. The y values look like they're getting close to 2. And we're seeing that because the decimal parts are all squeezing in on 2. And even though this 10 to the 6th one is actually slightly bigger than 2, to 5 decimal places we can't really see that. Okay, so what we would expect here is that the limit as x goes to infinity of this function is 2. Now, why is it 2? There's sort of a couple ways to answer that. The first is this numerical experimentation has led us to expect that it's probably 2, but there is an analytic technique that we'll learn in class for how we can prove that this is in fact correct. The downside to this numerical technique is what's to say that the true answer isn't supposed to be 2.00001 or something like that, and that we're just missing that last digit because we've been rounding numbers here. So there is a way for us to tell that 2 is in fact right on the nose the answer, and we'll talk about that technique a little bit more in class. Now the other thing that we want to deal with here is notice that this is kind of a special function. It's a rational function, and we've kind of looked at these before, the rational functions anyway, when we were talking about horizontal and vertical asymptotes. But we can still ask this question: what is the limit as x goes to infinity of a function, even if it's not a function like this, even if it doesn't have, it's not a rational function. So if there's square roots or something in it, then we might still want to be able to ask this question, but how we deal with that may change. Okay, so sort of the recap here. We're interested in the long-term behavior of the function, meaning for really, really large input values of x. And in this case, we noticed that we got 2. Right. Now, you probably could have guessed that we would have gotten 2 as the limit just by looking back at the original function. In this case, the ratio of the leading coefficients is 2, and the degree of both the numerator and denominator are the same. And surprise, surprise, the limit comes out to be 2. So those sorts of tricks we learned back when we did the horizontal asymptote stuff. And for rational functions like this, they're all totally still applicable. What we'll be able to do in class is to demonstrate why that result is in fact correct. So why the trick that we learned back in the day actually does work. So that's what we'll talk about in class, and then we'll do some more exotic examples.